Hi, welcome to the 17th session on group theory. Uh, this, this Today's session will deal with isomorphism between groups. Probably it will continue one more session. Okay, let us get started. Suppose G and H are groups. Okay, a homomorphism F from G to H is an isomorphism if F is a bijection. That's it, as simple as that. So, when I want to say F and G are F is an isomorphism, two things I have to ensure, that it is a bijection and it is a group homomorphism. Therefore, a map F from G to H is an isomorphism if it satisfies two conditions. One, F is a group homomorphism, and two, F is a bijection. That is, it's on 1 and on 2. Okay. See, intuitively, isomorphic groups are the same. Okay. Some of you had been watching my videos seriously would have seen I had many times exhibited groups, okay, and they look like the same thing there, okay, and also I said it looks like they are in different disguise, okay. So we will just start with a very good example which I already mentioned, okay, and then we will go through the standard way algebra does these things. So a telling example is this. Okay, suppose my G is Z8 star, that is units in Z8, that we know they are relatively prime numbers under multiplication 1, 3, 5 and 7. So this is order of G is 4, right? Then what we found out was, okay, 3 squared is 5 squared is 7 squared because 9, therefore 1, this is 25, therefore 3 times 8 times plus 1, 49, 6 times 8 times plus 1, therefore all are equal to 1 in Z8. Z8 actually, right? Okay. And not only that, if I multiply 3 times 5, it is 15, that is to 7. And if I multiply 3 times 7, it's 21, that is 2 times 6, 2 times 8 plus 5, therefore it is 5. Okay, and similarly, let's say 5 times 7, that is 35, that is 4 times 8 plus 2, that is 2. That is, start with any two elements here between 3 and 5 and 7, and when you take the multiplication, the product is the third element, right? That is the product of any two elements in 3, 5, 7 is the third element. Okay, this is one example. Okay, let us look at H. Okay, in H, let us look at, this is the subgroup of S4, and what is H? H is consists of only these elements, the transposition 1, 2, the transposition 3, 4, and the cycle decomposition 3, 4, and identity. This again has 4 elements, and these are all, you can see, they all, okay, commute with each other. And again, you can see square of this is identity, and square of this is identity, and square of this is identity, and the product of any two from which one? 1 2 3 4 and 1 2 3 4 is the third element. Right? Now let's look at a third group K, okay, which is Z2 under addition and Z2 under addition. Okay, therefore what are the elements? The elements are 0 0, 1 0, 0 1 and 1 1. These are the only elements, right? And here it's a square is again 0 0. Remember, square here is 1 1 0 plus 1 0, that is 2 0, which is 0 0. Similarly, square is here 2 times, there, that is also 0 0, and the square of this is also 0 0, and the product of any two is the third element. Right? Now look at the descriptions. What was G? G was units in Z8, right? And what are the elements? The elements are 1, 3, 5 and 7, if I remember correctly. And what are the operation? It is a multiplication modulo 8. You multiply them and divide by 8, and whatever is the remainder is what you are producing. Okay, look at the elements look very different, and the operations also a little complicated. And let's look at the second one, namely the subgroup of S4, that is transposition 1 2, transposition 3 4, and the cycle decomposition 1 2 3 4. That's a permutation. Okay, here what are the elements? They look completely different. They are all parts of some kind of permutations of four numbers 1 2 3 4. The elements look very different, right? And what is the binary operation? Binary operation is the composition of maps, because when sigma is a permutation, sigma composite tau is composition of permutations, right? Because sigma is a bijection, tau is a bijection, therefore they are maps. Sigma composite tau is the composition of maps. The operation looks different. And let's look at the third one. Third one is Z2 cross Z2 with under addition. Okay, there also it's complicated. Okay, in each other, so any element is of the form some A comma B and another element C comma D. What is the binary operation? Binary operations is done component wise, A plus C and B plus D, right? That is addition modulo 2. Is that okay? So the description of the sets themselves are so different, and the binary operations are so different, but they all exhibit the same kind of behavior. Apart from identity, there are 3 elements, and each of the element is of, okay, square is identity, and take any product of any 2 elements, I get the third element. Okay, you see that we are abstracting. There is absolutely no difference between them, right? So we want to look at, okay, this is what exactly isomorphism tries to do. That is, you may not recognize something, they are the same, because they may come in disguise, and here the binary operation also look different. Okay, right. Let's go back. So what is the map? So the map is very easy. I can define F from G to H, or so let us say G from H to K, and similarly some H from G to K. All maps are obvious. Identity will go to identity because it must be a group homomorphism. Then it does not really matter in which way you send the elements. For example, in this, what was that? G was right. 3 can go to 1 2, or it can also go to 3 4. I don't care. 5 may go to 3 4, and 7 may go to 1, 2, 3, 4. Right? Similarly, H. Well, H was Z2 cross Z2, and this was no, H was S4. Yeah, right. Sorry, this is transposition, right? Yeah. Therefore, I can send identity to identity, and 1, 2 may go to K, which is 1, 0, and 3, 4 may go to 0, 1, and 1, 2, 3, 4 may go to 1, 1. Okay, and so on. I leave this as an exercise. You can see these are all bijections and homomorphisms, and hence they are isomorphisms. So pause, review, proceed. Right? Okay. Before we go further, let us say, to make a definition, suppose F from G to H is an isomorphism, then F is a bijection in particular, right? Therefore, F inverse will be a map from H to G, right? Because this is the inverse of F. Because F is a bijection, it has an inverse, right? Now I claim F inverse is a group homomorphism. Notice that since F is a bijection, F inverse is also a bijection. And if I say F inverse is a group homomorphism, then F inverse is an isomorphism. Right? So we need to prove this. Right? That's very easy. Right? Let us look at. So let us look at F inverse of H1 in H2. Right? Now what is H1? H1 lies in H. Since F is a bijection, there is a G1 such that F of G1 is H1. Similarly, F of Gi equal to Hi. Right? Is that okay? Right. Now let us look at. So I have to check whether it is a group homomorphism, right? That is whether I have to check whether this is equal to F inverse of H1 into F inverse of H2. Is that okay? Right. Now what is F inverse of H1 H2? Let us look at an example so that you will know. This is my G, this is my H. Okay, I have Y1, I have Y2, I have H1, H2, G1, G2. Right? Now, where do you think this is? Let us look at G1, G2. Where do you think it will go under F? Right? I know where does it go. Where does it go? It goes to F of G1, G2. Since F is a group homomorphism, it will go to F of G1 into F of G2. That means it goes to H1, H2. Right? Therefore, what is F inverse of H1, H2? By definition, it is G1, G2. But what is G1? That is F inverse of H1. What is G2? F inverse of H2. So we proved it. Right? Therefore, if F from G to H is an isomorphism, then the inverse of F, namely F inverse from H to G, is also an isomorphism. Okay, pause, review, proceed. So that means I can very easily define, given two groups G and H, I say simply they are isomorphic if there exists one group isomorphism between one to the other. I don't even know to say which way. Do you follow that? If I want to say G and H are isomorphic, I have to find either an F from G to H which is an isomorphism, or I have to find a G from H to G, which is an isomorphism. That's enough for me. You understand? Right? Whereas the earlier one, when I say F from G to H is an isomorphism, then I may be able to say only G is isomorphic to H. I may not be able to say other way around. Are you following? Please understand this. Okay. And immediately this follows that, okay, being isomorphic, okay, suppose G, let me say denote this by H, okay, this is the note isomorphic. Okay, this is the standard notation. That means there exists some isomorphism from between G and H. Okay, whenever there is an isomorphism from G to H, there is also the inverse will be an isomorphism. It may not be unique, there may be many, right? And suppose H is, therefore, being isomorphic, okay, is a reflexive relation. That means G is isomorphic to G itself, because identity map will do. It's an isomorphism, right? And if G is isomorphic to H, then if only if H is isomorphic to G, because if F is an isomorphism from G to H, then F inverse will be an isomorphism from H to G, right? Therefore, this means it is symmetric. And the next one, it is transitive. That is, suppose G is isomorphic to H and H is isomorphic to K, then we want to claim G is isomorphic to K. That is very easy. Look at that. There is a bijective map from G to H and there is a bijective map H to K. These are isomorphism, right? Therefore, G composite F is a bijection from G to K. Yeah, bijection. And also, composition of homomorphism is a homomorphism also. Composition of homomorphisms. I don't think I proved it. Why? So I don't need it to be isomorphism, okay? Now what I am claiming, G to H is a homomorphism and H to K is a homomorphism. Then G composite F from G to K is a homomorphism. K. That is very easy because G composite F, let AB belong to G. Okay, AB by definition G of F of AB. But what is F of AB? Since F is a group homomorphism, that is FA into FB. This is the binary, this is the product in H. Now G is a group homomorphism H to K. Therefore, this is going to be G of F of A times G of F of B. That is same as saying G composite F at A, okay, this object into G composite F at B, this object, right? This we have to prove G composite F at A, the whole thing, dot G composite F at B, the whole thing. Are you following? Call this, we want to call phi. Phi of A is phi of A into phi of B. What is phi of A? G composite F at A. That's what we proved. Yeah. Therefore, we have proved being isomorphic, this relation is symmetric, reflexive, symmetric, and transitive. Some of you know who know the words etc. You will wonder why I never said it's an equivalence relation. Equivalence relation is defined on a set. Now what is the set we have to consider? Then you don't call set of groups, you call it class of groups. Okay, that's a slightly trickier issue. So I will not go into that. I will simply say being isomorphic is that relation is reflexive, symmetric, and transitive. Okay, good. Now let's look at some concrete examples. So let's look at some examples now. This example 2 is, let's look at some simple example from, let us look at additive group of reals and multiplicative group of positive reals. This is positive, not non-zero, positive. They are isomorphic. This we had already seen, right? We wanted a group homomorphism. The obvious thing was define f of t equal to exponential t or e power t, right? Then we know that this is 1 1 on 2 using this analysis, but we are going to assume the inverse f inverse is of x. Let elements here will be xy and here st etc. Okay, elements x, f inverse x will be log of x. Remember, this is a natural logarithm. What Americans write as ln of x, natural logarithm, right? That's a bijection. And we know that this is a group homomorphism. S plus t is e power s plus t, that is e power s into e power t, that is fs into ft. Whereas the inverse is log of xy, the product here is going to be log x plus log y. Okay, therefore these are isomorphic. Okay, now let's look at the third example. Now let g equal to h equal to this. Okay, and fix a natural number n, okay, greater than or equal to 1. Okay, n in n. Okay, let us look at our group my hn to be n times z. That is all multiples of n. Then I claim, okay, g and hn are isomorphic. This we had already seen, because you give me any k z to nz, okay, k go into n times k or kn. Okay, this is an isomorphism. Okay, so pause, review. Just to appreciate that, do that, my n could be something like trillion or a million. Alright, so it is a something very proper subset of that, but we have an isomorphism, natural map which you can think of actually turns out to be group homomorphism, and hence it's an isomorphism. Okay, right. Now we can ask for the next question. Okay, how about q with under addition and q star? If you want positive or anything, I don't care. Yeah, dot product. Okay, are they isomorphic? If you have watched my videos earlier, we have said that we had already proved there exists no onto map onto group onto homomorphism. There exists no homomorphism f from q plus onto q star, right? But remember, if they are isomorphic, what does it mean? There is a group homomorphism which is bijection. In particular, it's onto. There is a group homomorphism which is onto, right? If they are isomorphic, then there exists a homomorphism which is bijection. In particular, a group homomorphism which is onto. But we already proved there exists no group homomorphism. The way we did that was, suppose f of a equal to 2, then f of a by 2, okay, what will be? F of a by 2 times f of a by 2 will be f of a, that will be 2, but f of a by 2 has to be in q star. In particular, it's a rational number whose square is 2. That was a contradiction. Okay, please recall. Okay, this belongs to q and whose square is 2. Okay, that is absurd because we know there exists no rational number whose square is 2. Right? Okay. Now, so let's look at some more example. I think this is a fourth example. Fifth. Suppose let's look at just to become that. And now let's just ask some questions before going to that. Suppose G is abelian and H is non-abelian. Can they be isomorphic? No, because we have seen f of G is abelian. If f is a group homomorphism, then f of G is abelian subgroup H. But right, if f is an isomorphism, then f of G equal to H. If f is an isomorphism, H. Okay, but this has to be abelian, but we know this is non-abelian, a contradiction. Therefore, an abelian group and a non-abelian group cannot be isomorphic. Okay, and the second question, suppose G is non-cyclic and H is cyclic, can they be isomorphic? Now think for a minute. Okay, you had already seen, what have you seen? If G is cyclic, F is a group homomorphism, the image of a cyclic group under a group homomorphism is cyclic. You understand? Now I am asking, G is non-cyclic, H is cyclic, can they be isomorphic? Somehow I want to make use of the result. So what kind of isomorphism will I consider? Will I consider an isomorphism from G to H or H to G? Do you understand? Learn to think like that. Okay. Suppose they are, then there exists F from H to G, which is a group, which is an isomorphism. Right? Hence, f of G, H equal to G must be must be cyclic. Okay, this is a contradiction. Therefore, a non-cyclic group and a cyclic group cannot be isomorphic. Right? Now let us make use of this to solve the next problem. Let us look at, okay, let us look at Z10 star, that's units in Z10, and Z12 star, that is units in Z12. First notice that if they are finite, right, if G and H are finite and the number of elements in G is not equal to number of elements in H, then G and H cannot be isomorphic, because, right, there cannot even be a bijection and hence there cannot be bijective group homomorphism. Is that clear to you? Right. So let us see, these are finite, therefore first I have to make sure they have the same number of elements. Do you understand this? Yeah? Fun, right? Okay, let's do it. What is this? This consists of all elements which are relatively prime to 10. That is, of course, 1 has to be there, and 2, 3, 4, no, 5, no, 6, no, 7, yes, and 9. Right? Is that okay? Right. I hope there are only 4 elements, 9, right. And this Z here, the elements are going to be, 1 has to be there, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Is it okay? Right. Now let's look at, okay, what is 3 squared? So they have exactly 4 elements. Therefore, there could be a bijection. Can there be a group homomorphism which is also a bijection? That's a clear. Right? Let us see. What is 3 squared? 3 squared is 9. 7 squared is 49. That is also 9. And 9 squared is 81. That is 1. Am I doing it properly? So I have 3 squared, 3. 3 squared is 9. Let us see 3 cubed, 27. 27 is 7. Right? And 3 to the power 4 is 7 into 3. That is 21. That is 1. Therefore, I have 3, 9, 7 and 1. That is the entire group Z10 star. Therefore, this is cyclic because Z10 star is generated by 3. Right? So, now let's look at Z12 star. Right? What are the elements? 1 and 5, 7 and 11, I guess. Yeah. Now, what is 5 squared? 5 squared is 25. Yeah. 25 is 1. And what is 7 squared? 48. That is 1. And what is 11 squared? 121. That is also 1. Right? So, now, therefore, this is not cyclic. Therefore, Z10 star is not isomorphic to Z12 star. Have you seen Z12 star somewhere? Yeah, right. It is exactly like Z8 star which you saw earlier, or Z2 cross Z2, or the transposition 1 2, the transposition 3 4, and the cycle decomposition 1 2 3 4. Right? Same group. So how many things, different avatars, the same group can appear. So that is where the isomorphism comes in. Okay, and in this case there is one more reason to say that also I will do that. One of the ways to look at, okay, how to show non-isomorphism, that is given two groups G and K, which you want to say non-isomorphic. One of the ways is number of elements is not the same as number of elements in H. Okay, that may be one reason. The second reason, suppose there may exist an element A in G whose order is n. If there is a group homomorphism F from G to H, then what will be the order of A? This will again be n. Why? Because remember, order of F of A must be a divisor of order of A. Right? Now F inverse from H to G is also group homomorphism. It's an isomorphism in particular group homomorphism. Therefore, if let's look at F of A, where does it go? F inverse of F of A is A. Right? Therefore, call this as 1B. Okay? Right? Therefore, order of F inverse of B, which is order of A, must be a divisor of order of B, which is order of F of A. So you can see each is the divisor of the other, therefore they are equal. You understand that? Yeah, pause, review, proceed. Therefore, one way of saying, okay, G and H are not isomorphic maybe to find some element A in 1 and its image, okay, say its order is n, and say that there exists no element in H whose order is n. For example, okay, let's look at Z4 and Z2 cross Z2. Both are abelian groups and 4 elements, but here I know 1, okay, order of 1 here is 4. Okay, here order of either 0 0 is 1, order of any element 1 0, order of 0 1, order of 1 1, they are all 2. Therefore, they cannot be isomorphic. Yeah. So these are the things. So these are the ways, in various ways things occur. Okay. Now we want to look at something a little more interesting. We had two groups G and H. We wanted to see isomorphisms. We looked at some examples. Right. There are a lot more examples, but if I keep on giving, you can already see we are in the 17th session. Usually group theory must have been over in the course by then. Anyway, so let us go through. So yeah, what is the question? Yeah. Now suppose I have a group G. I want to know whether I can have an isomorphism from G to G itself. G is of course isomorphic to G, namely with the identity map. So what is the question I am asking? I am asking whether there exists non-identity isomorphism from G to G. Is the question clear? Let us see. Okay. Suppose G is an abelian group. Right? We had already seen the map f of A equal to A inverse is a group homomorphism. Right? Seen already. Right? It's also a bijection. Right? Because f of A equal to f of B if and only if A inverse is B inverse. Right? But what does it mean? The why does it imply A equal to B? Do you understand the question? All of you may immediately say it's clear. Okay, there is a subtle argument. See, if A inverse is equal to B inverse, notice that the inverse of A inverse, what is it? It is A. And inverse of, therefore, inverse of B inverse is B. But since these two are equal, the inverses are unique and therefore A and B must be the same. But our assumption is that. Okay. If A is not equal to B, then there is a contradiction. Or if you prove if f of A equal to f of B, then A inverse is B inverse, and hence that happens if only if A equal to B. Therefore, it's 1 1. Of course, it's onto. Why onto? Okay. Give me any element x in G and take A equal to x inverse. Then f of A is x inverse will be x. Therefore, this is an isomorphism. Okay. Pause. Review. Proceed. A question I can ask is it different from the identity isomorphism? Okay. So let f be from G to G. G is again abelian. F of A is A inverse, and let I be the identity G to G, where I of A is A. So if f equal to I, if and only if for all a in G, f of a must be equal to I of a. That is if and only a for all a in G, f of a is a inverse must be equal to I of a is a. That is for all a in G, I must have a squared equal to identity. Multiply both sides by a, then I get a squared is identity. Right? So if in G, okay, a squared equal to identity for all a is happens, then F is identity map. We have not proved F is not a non-identity homomorphism. Do you understand that? So essentially, every element is of order 2, of course, barring the identity. Okay, every non-identity element is of order 2. Okay, then we had already seen that group is abelian, and the map inversion map is anyway an isomorphism, but that isomorphism turns out to be the identity map. Yeah, have you seen such an group? Yeah, just now we saw U star of, sorry, Z12 star, Z8 star, and Z2 cross Z2. All of them had that problem. Yeah, so the the inverse map is the identity map. It's not a new map. Do you understand this? Yeah. Okay. So let me go through one more example, and we had already seen that example, but let's go through it. We have to check whether it's an isomorphism now. So the last example is, suppose G is any group A in G fixed. Let us look at FA of G. This is A, G, A inverse. This is what we call conjugation by conjugation of the element G by the element A. So we already know it's a group homomorphism. We have seen FA from G to G is a homomorphism. Already seen. Okay. So, and remember, for given A, FA will be different from other. Okay. If A and B are different, FA may be different from AB. Right. The first thing is I want to know, when is FA identity? That we are already seen. FA is identity meaning what? FA at G must be equal to identity at G, but FAG is A, G, A inverse, that must be equal to G. So multiply both sides on the right by A, that AG, A inverse A equal to GA, that is AG equal to A. This is for all G. Right? So what does that mean? This means A lies in the center of the group. Right? So pause, review, proceed. In particular, suppose G is abelian, then every A in G is in the center, because center is itself, the group itself, right? Therefore, again in the abelian case, these maps FA are not going to be any different. We will again get the same identity isomorphism. Is that all right? Okay. So before I stop, it's only about 45 minutes. Okay, I will take few more minutes. In fact, I should be able to prove it in 15 minutes, but it's slightly offbeat. Let us do that. Okay. Is there anything else I would like to say? Yeah, okay. Now let's look at this map. Okay. Let G be a group, A in G fixed. Let us look at now lambda A from G to G. So lambda A of G is AG. Lambda for L and L for left. So I am multiplying on the left. It's a left multiplication by A. That's why lambda A. Is that clear? This is never a homomorphism unless A is identity. If A is not identity, then it's never a homomorphism, because if it's a homomorphism, lambda A of identity must be A times identity, which is A, right? But A is not identity. You understand that? Therefore, this is never a homomorphism. Okay, if A is not equal to identity, lambda A is not a homomorphism. But I claim it's a bijection. Lambda A from G to G is a bijection. Why? Let us look at. Is the 1 1? Suppose lambda A of X equal to lambda A of Y, where X and Y are in G. This happens if only Ax equal to Ay. Since these two elements are equal, I can multiply both of them on the right by A inverse. A inverse Ax should be equal to A inverse Ay, but that is by using associativity, etc. That is X equal to Y. Therefore, lambda is 1 1. And lambda A is onto. Why? Because if you give me a Y in G, I want to know whether there is an X in G, so that lambda A of X equal to Y. Right? But what is this? This is Ax equal to Y. What is unknown? Y is given, A is already given, therefore X is unknown. So how will I find Ax? Right? Multiply both sides by A inverse. Therefore X is A inverse Y. Right? Remember, A is a group element, therefore A inverse is a group element, Y is a group element, the product is a group element, they all live in G. You understand that? Therefore X is an element of G. Now just to multiply this, lambda A of A inverse Y, by definition A into A inverse of Y, but that is A inverse of Y, but EY, which is Y. Therefore the lambda map is 1 on 2. Okay. So what have we shown? For every A in G, the map lambda A from G to G is a bijection. Okay. Notice that it is immaterial whether G is finite or infinite. Do you understand that? Now, lambda A, think of it as just a map from the set G to the set G. Because anyway, it's not a group homomorphism, so I should only think of a map. It's a bijective map from the set G to set G. Right? Have you seen something about them? What have you seen? You have seen that the set of bijections of a set form a group under composition. Yeah. So I can actually ask for what happens to this map. Okay, let me write it so that you don't get confused. So therefore lambda A belong to a sub G. What is this? This is set of bijection. Of the set. Okay, I am not thinking of group structure here. Right? Now I know SG is a group by itself under composition. Therefore, I have a map phi from G to S of G. What is the obvious map? Take any element A. Where does it go to? It goes to lambda A. That is, phi of A is lambda A. Okay, pause, review, proceed. Right, we have found something very interesting. What have we found? We have what you call left translation. You call it left translation or left multiplication is a bijection of the group. Fix an element A in G. Look at the map lambda A, which is left multiplication by A. That is G going to A times G. Okay, it's not a group homomorphism unless A is identity, but it is a bijection. Therefore, given any A in G, I have a bijection lambda A in S sub G. What is S sub G? The symmetry group of G, that is set of all bijections on G under composition. Right? Now I have a map A going to lambda A, and the domain is G, which is a group. The codomain is S sub G, which is a symmetry group on G, which is also a group. So what is the next question I should ask? Yeah, whether it is a group homomorphism. Yeah, we will look at it, then stop. Okay, then you will see something may not work, but you try to be creative. Okay, his question is, yeah, let us see. So what is phi of AB? Phi of AB is lambda of AB, right? So I want to know, what I want to know is phi of AB equal to phi of A composite phi of B. Remember, phi of A is an element of S of G, phi of B is an element of S of G. What is the binary operation here? It is a composition of linear maps. You understand? But what is this? This is lambda A composite lambda B. And what is this? This is lambda AB. The question is whether they are equal. This is a question. Right? So when are two maps equal? Many times you have seen for all x in G, I have to check whether lambda AB of x equal to lambda A composite lambda B of x. Right? But what is lambda AB of x? That is ABX. What is this? Lambda A acting on lambda B of x is BX, but that is ABX. Right? Because associativity is same as ABX. Therefore, phi is a group homomorphism. Now, if you are a fair-minded guy, okay, you should ask the next question. Anyway, lambda A is never meaning, but for the trivial case, never a group homomorphism, multiplication by on the left. So why you are being unfair? You are doing only multiplication on the left. Why can't I multiply on the right? Right? So then again I can ask whether it is a bijection. Call it a row A, row for R for right. Row suffix A, that's a map. The map is row suffix A of G is G times A. Right? Whether it's a bijection, that's very easy to check. It's a bijection. Okay. Therefore, I have a map now xi, which is A going to row of A. Whether it is a group homomorphism. Okay. So, right, multiplication, row of A from G to G, okay, row of A of G is G. Okay, check this is a bijection. Okay, exercise. This is easy. Okay, Now let me call xi from G to S of G. What is the map? Xi of A is rho A. Now what is that I want to know? Whether xi is a group homomorphism. That is xi of AB equal to xi of A comma xi of B. But psi of AB is rho of AB, whether it is equal to rho of A composite rho of B. Right? So let us answer this. Okay. When are they equal? Rho of AB of X is XAB, and rho of A composite rho of B of X is XB, right? Rho of A XB, that is XBA. So rho of AB is not equal to rho of A composite rho of B. That is, psi is not a homomorphism. That's something unfair, right? Yeah, it's something unfair. What do I do? Remember, when I look AB, it comes as BA. Do you think of some group operation which has something like that? The order is changed. Maybe a little difficult, but some of you may be. And if you've seen it, you will say that. If you have not seen it, you should think. The obvious thing is you define rho of A acting on G is not G times A, but G times A inverse. Let us see what it means. Okay, so modify. Rho of A G is GA inverse. Then what is the rho of A of GB? This is G AB inverse, that is G B inverse A inverse. And what is rho of A composite rho of B acting on G? That is rho of A acting on rho of B acting on G, but is rho of A acting on rho of B acting on G is G B inverse, and this acting on is G B inverse A inverse. Right? Now if I define xi from G to xi of A equal to rho of A, where rho of A is defined by this is a homomorphism. I'm sorry, I forgot to share in my check. Let us do that quickly. So we modify rho of A G equal to G into A inverse, then rho of AB G is G times the inverse of AB, that is G times B inverse A inverse. We are going by definition, right? Call C AB as C, then C G times C inverse. But what is C? C is AB, therefore C inverse is B inverse A inverse. It's clear? Now what is rho of A composite rho of B on acting on G? That is rho of A acting on rho of G acting on G. But rho of B acting on G is GB inverse. Therefore rho A acting on that will be GB inverse A inverse. Therefore, okay, xi is a group homomorphism. I hope you enjoyed. Yeah, some of the things, you should not lose heart. Something looks very similar. Okay, you should still further think of modifying slightly so that things work out. Therefore, there is fairness. Okay, this is something much more what is related. Okay, there is a notion of opposite group. I don't want to kind of bother you with too much of jargon. Let's stop here. I hope you enjoyed. Okay, and the next question I want to know is whether this map is 1-1. Okay, why it matters, we will look at it in the next session. Okay, I hope you enjoyed. Keep tuned. Okay, stay tuned. We will meet again.